Hi everybody, I'm Archana. Two of my friends, Madhurima and Sairaj, we are going to talk about compression and its applications. This is the overview of our presentation. First, we are going to see what is lossless compression. In that lossless compression, I'm going to talk about Huffman coding, and Sairaj is going to talk about LZ77. Then we have lossy compression, and Madhurima is going to talk about DCT algorithm. So first, let's see what is compression algorithm. Compression algorithms are the different techniques to reduce the number of bytes required to represent data and the amount of memory required to store the information. So it is used for reducing the size of data or message. Suppose you want to store data in a file, so you can save data in a compressed form to reduce the size of a file. When data is sent over a network, data can be compressed and sent to reduce the cost of transmission. So there are two components of compression. One is encoding and another one is decoding. Encoding algorithm takes a message and generates a compressed representation, while decoding algorithm reconstructs the original message from the compressed representation. So these two components are typically tied together since they both have to understand and share the compressed representation. And we have two categories of compression. One is lossless compression and another one is lossy compression. In lossless compression, uh, it can reconstruct the original message exactly from the compressed message. Lossless compression are typically used for text, while lossy compression it can reconstruct an approximation of the original message. Uh, and lossy compression are typically used for images and sound, where a little bit of loss in resolution is often acceptable. So I'm going to talk about Huffman coding. So it is proposed by Dr. David A. Huffman in 1952, and it is a method for construction of minimum redundancy codes. So in this presentation, I'm going to explain you if a normal message is sent, what will be the cost, and what is the fixed size encoding, and what is variable size encoding, that is Huffman coding. Now let us study the problem. I have a message here. So this is the message. This message, I want to store it in a file or I want to send it over a network. Then let us understand what is the cost of a message. The cost of a message is measured in terms of bits. Let us check the length of the message. So the length of the message is 20. Next, how this message has to send. This has to be sent in a ASCII code, and ASCII codes are 8 bits. So if I say A, its ASCII code is 65 and this is its binary representation. Similarly for B, 66 is its ASCII code and this is the binary representation. Likewise, for C it is 67, D it is 68 and E it is 69. So without compression, the size of the message will be 160 bits. How? ASCII codes are 8 bits, so 8. And then the length of the message is 20. So the original size of the message without any compression, it will be 160 bits. Now let us see, can we use our own codes instead of ASCII codes? How it is possible? See, I'm not using all English alphabets here. I'm using just five alphabets, that two capital letters. Do I need 8-bit code to represent just five alphabets? No, few bits are sufficient. And can I use my own codes with less amount of bits? Yes. So now we will see fixed size codes. Here I have taken alphabets from the message and how many times each alphabet is appearing. I have written the count here. Also, you can call it as frequency. So A is appearing 3 times. Likewise, you can check for all. So how many times they are appearing? I have written here. Total, there are 20 alphabets. If you want to take frequency, then you can say 3 by 20, 5 by 20. Now let us see what should be the code. See, I have just 5 characters, and I don't need 8 bits for just 5 characters. 8 bits ASCII codes are for 128 characters or 128 symbols. But for 5 characters, let's see. If I have just 1 bit, uh, what is the maximum number of character that I can represent? So if I have 1 bit, then I can represent 2 characters, that is 0 for one symbol and 1 for another symbol. What is the maximum number of characters that I can represent if 2 bit exist? So if there are 2 bits, then 4 characters can be represented. How? 0, 0, 0, 1, 1, 0, and 1, 1. And each combination represents one symbol. So in this message, we have 5 characters. So 3 bits are sufficient to represent all 5 characters. So if I take 3 bits, then how many combinations are possible? 0 to 7. That is 8 symbols we can represent. But we just need 5 out of 8. So I'll say 0, 0, 0 for A, 0, 0, 1 for B, and 0, 1, 0 for C, and 0, 1, 1 for D, and 1, 0, 0 for E. Uh, when message is encoded using this one, then what will be the size of the message? As we know well that there are 20 characters and each take 3 bits, so this will be 20 times 3, it will be 60. So encoded message will be 60. So size of the message will be 60 bits. And one important thing we cannot neglect. What is that? When I'm sending a message, suppose encoded in this one, how the receiver will know what are the codes? Even if I store it in a file and later I want to retrieve, how do I remember what are the codes I have used? Is 000 means A. See, to make it easy, I have taken alphabets A to E here. But alphabets are anything here. This can be A, this can be M, this can be O. Then how I can know which code is for what? So I should also have codes, that is the table also along with the message. The message is 60 bits and you also need table that helps to decode this message. So let us see how you have to send this one along with the table and what will be the size. So see, I have 5 alphabets. This alphabet should be in an original form. Now standard is what? ASCII codes. So I must write ASCII codes for all these 5 characters, and for this 8 bits for one character. So how many characters are there? 5 characters, and each is 8 bits. So 5 times 8. So this will be 40. 5 times 8. Uh, then total how many codes? So we have total 5 codes. And how many bits for each code? 3 bits for each code. So for codes, it is 5 times 3. So for codes, it is 5 times 3. So it is 15 bits. So total table size will be 40 for characters and 15 for codes. So total it became 55 bits. Then what is the size of original message? So it is 60 bits. I mean encoded message. It is 60 and 55 bits from for the table. So total it will be 115 bits after the compression. See, without compression, the size of the message was 160 bits. Now it has reduced to 115 bits. Still, we can reduce the size of the message. Now we will go to a variable size code and let us follow Huffman coding, which will still reduce the size of the message. Huffman says that we don't have to take the fixed size code for the alphabet. Some character or alphabets may be appearing few times or few may be appearing more number of times. So if you give small size code for the more appearing characters, then size of the entire message will be definitely reduced. So let us see what is his idea. So already I have taken the table here. So these are the characters and how many times they are appearing. That is the count I have written. Now Huffman code follows optimal merge pattern. Now we have to generate our own code. So what should be the method for code? So Huffman has given a approach for getting our own code. That is a variable size code. So he says that all those alphabets should be arranged in increasing order according to their codes. So first will be the smallest and last will be the highest. So in this, which one is the smallest? So E is the smallest because it has appeared only 2 times. So here I have written first is E. So second highest number is 3. So next is 4, next is 5, next is 6. So I have written here, and we have to follow optimal merge pattern. So what I should do in optimal merge pattern, we should merge two smallest one and make one node. So we have a node 2, 3, 4, 5, and 6. So which are the two smallest nodes? 2 and 3 are smallest. So combine these two nodes and make it a single node. So 2 plus 3 is 5. So I have made it a single node. Now we are left with 5, 4, 5, 6. Among 5, 4, 5, 6, which are the two smallest nodes, 5 and 4. So here is the 5 and here is 4. And we also have 5 here. So you can merge any two nodes, but I have taken these two nodes and I have combined and made it a one node. So 5 plus 4 is 9. So I have written 9 here. Now we are left with 9, 5, and 6. So among 9, 5, and 6, 5 and 6 are the least two nodes. So I have combined these two nodes and made a one node. So this node will be 11. Now we are left with 9 and 11. So combine these two nodes and make it a single node. So 9 plus 11 is 20. So this is the last node I have written here. Now this tree help us to define code. How? On the left hand side, mark them as 0. So I have marked it as 0. And on the right hand side edge, mark them as 1. So this will be the right hand side. So I have marked it as 1. Now what are the codes? For each alphabet, follow the path from root onwards. So for A, it is 0, 0, 1. For B, it is 1, 0. For C, it is 1, 1. For D, it is 0, 1. And for E, it is 0, 0, 0. So I have written here. That's it. These are the new codes. Now you can see some codes are 3 bits. So A is 3 bits, E is also 3 bits, and some are 2 bits. So variable size codes, I can use these codes for encoding the message. Like for B, it is 10. If it is A, I should write as 001, like likewise. If I use these codes, then what will be the size of my message? For that, how many bits are there for A? 3. And how many times A is appearing? So A is appearing 3 times. So 3 times 3, it gives 9. Then for B, how many times B is repeating? So 5. And how many bits are there for B? It is 2 bits. So 2 times 5, 5 is uh, the count and 2 is the number of bits. So it will be 10. Therefore, total number of bits are 45 bits. Therefore, message size is 45. Along with message, I should also send table. Then only decoding can be done. Now let's see what will be the size of the table. All these alphabets, I should send the ASCII code. So 8-bit of ASCII code and 5 alphabets. Therefore, 8 times 5. And codes also I should send. So this code when they are stored, so how many codes are there? So totally there are 12 codes. You can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So totally there are 12 codes. So together 40 plus 12. So the table size, the characters size is 40 bits and codes are 12 bits. So totally the table size became 40 plus 12. It became 52. Now we can calculate the total message size, 45 from encoded message and 52 from table. So total it became 97 bits. So without compression, it was 160. Then it reduced to 115 when we used fixed size encoding. After using Huffman encoding, the message size became 97 bits. So if we have table, we can easily construct tree and decode the message. In this way, message can be decoded and we can get back the original message. So the receiver can convert message into ASCII character and use it in the machine. While using it, it will all not only using the code, it has to convert into ASCII code. Like when you have a zip file or compressed file, you cannot use it as it is. You have to decompress and use it. Similarly, you have to decode and uh, use the message. So this is the running time. The time efficiency of building Huffman tree will be big O of n log n. uh, that's it about Huffman coding. Now my friend will continue. Thank you.
Thank you, Archana. So I am Sairaj and I'll be presenting the LZW compression algorithm. So what is LZW? It stands for Lempel Ziv Welch after the name of the creators. LZW is a lossless compression algorithm and hence no data is lost during the compression process. The algorithm is very simple to implement and it has the potential for very high throughput in hardware implementations. The main foundation of the LZW algorithm is the reoccurring patterns. These reoccurring patterns are saved with a smaller character in order to save the data. It is an important technique for general purpose compression as it is very simple and versatile. So how does the algorithm work? First of all, the LZW reads the input as a sequence of symbols. The next step is to group the symbols as strings. Now the strings are converted into codes and these codes are stored in the code table. Since the code takes up less space than the strings they replace, the compression is achieved over here. Let's look at the characteristic features of the algorithm. In LZW compression, a code table is used. The common choice for the number of entries in the code table is 4096. So the codes from 0 to 255 are assigned to the code table, which represent single bytes from the input file. During encoding, the table contains 256 entries initially, with the other places in the tables are blank. The compression is achieved by using codes 256 through 4095 to represent the sequences of bytes. LZW will recognize the repeated sequences and will add them to the table. Decoding is achieved by taking each code from the compressed file and translating it through the code table to find what character or characters it represents. So this is the pseudocode for the encoding of LZW. So first of all, we initialize the table with the single character strings. Then we read the input string and create a variable with the first input character. Now we define a new variable with the next input character. After that, we check if the first input character plus the second input character is in the string table or not. If it is already in the string table, then we check for the next character. But if it is not in the string table, then we output the code for the first input character and then add the first and the second character to the string table. And then set the first input character variable to the second input character variable. This is how we achieve encoding of the input. Now let's take a look at the decoding. So this is the pseudocode for decoding of the LZW. First of all, we initialize a table with all the single character strings. Then we initialize a variable for the first input code. And we use the output translation of the same variable. Now for every input code in the input stream, we initialize a new variable for the next input code. If the new variable is not in the string table, we initialize a variable and assign the translation of old to it. So hence here S will be equal to S plus C, else the S will be the translation of new. Here C would be the first character of S and then old plus C is added to the string table. This is how we recover the encoded input and we get the original string as an output with the help of the code table. Let's take a look at an example. Here, the given string is banana underscore bandana. So the first step is adding all the single characters into the table, like E to 0, B to 1, D to 2, and so on. Now, as we go along the table, we look for new sequences from the string. Whenever we find a new sequence, we add it to the table. If the string is a reoccurring one, then we continue looking until we find a unique string sequence. Now, once we go through the whole input, we will get an encoded code, which we will further use to decode and recover the original input. Here, as we can see, we got an encoded code equal to 1036045328. We are going to use the same code to decode and get the original string back. Now let's see how we can decode it. First, we take the encoded code on the left-hand side and then add the corresponding character to the partial sequence column. We start the index from 5 as we already have 4 single characters in the table. Now, as we go along the encoded code, we add the partial and the next occurring character to the entry column. Then we add the starting characters to the next partial entry. We keep repeating this step until the end of the encoded code. This way, we can decode the initial input value and hence the compression is achieved over here. Now let's take a look at the applications of the LZW algorithm. The first is image processing. So image is nothing but a representation of pixel values in a 2D array. Now consider this image with the pixel values given. In this image, there are many pixel values which are redundant. Like for example, the sequence of 87 is repeated for 4 times in the first row, and similarly it is repeated in the last row as well. So LZW focuses on the spatial redundancy and how to reduce the storage memory of this. It will assign a fixed length of word to a variable length sequences. In this case, there are similar pixel values in sequence which can be assigned to a fixed character or characters. So assigning a fixed length words will save the memory to store large number of pixels, and hence LZW proves effective in image compression. The next is LZW in Global Navigation Satellite System or GNSS simulation. The preservation and transmission of the large amount of data generated by GNSS is a complex and time-consuming task. This problem is solved using data compression, and LZW algorithm is the most widely used compression algorithm. In this, a higher rate of compression is achieved using an improved LZW. Different methods are used to attain improved compression effects by first increasing the capacity of the dictionary, second storage with variable length code, and next is using hash function to find strings. In this way, a large amount of data can be compressed using the LZW algorithm. Thank you.
I'm Madhurima. From here, I'll continue the presentation. Lossy compression. What is lossy compression? It is a form of compression that throws away some of the data without any noticeable differences from the original image in order to save space that cannot be absorbed by the end user. In lossy compression, the data in a file is removed and not restored to its original form after decompression. Data is permanently removed, which is why this method is also known as irreversible compression. This data loss is not usually noticeable. Example of the lossy compression is the JPEG compression algorithm. Here we have an uncompressed image on the left side which uses 216 KB of space, and on the right we have the same image as a compressed JPEG and it uses 38 KB. 82% reduction in file size, but the reduction in quality is not perceivable to a human eye. Let's take a deep dive into the JPEG algorithm and see how images can be compressed to just a fifth of their uncompressed file size, all while keeping the same image resolution and a very high quality appearance. Before moving on, let's understand the importance of JPEG algorithm. First, most digital images from your phone or camera are saved using JPEG format. Second, 86% images can be stored in JPEG formats when compared to other formats if you browse in internet. Here is an image with a little more than 210 KB, but with JPEG compression the actual file is only 38 KB. Same number of pixels but only 18% of the expected size, and the image produced still looks beautiful. This is the magic of the JPEG compression. JPEG aggressively takes advantage of the several clever ideas of the seemingly ridiculous amounts of compression with minimum effects on the quality of the original image. The number of pixels stays same, but eventually we get these defect squares which are called artifacts. Let's see how these images are compressed in the next slides. We start with an RGB representation of an image and then we encode it using a compression algorithm. This is what we store in memory and it's more compact but quite different than our original RGB representation. Compression scheme requires also defining a decoding component that converts the stored representation of our data into the RGB format that a computer can render as an image. Part of the JPEG standard is defining how both encoding and decoding work. A key point in JPEG is that the final decoded image is not going to be the same as the original uncompressed image. That's why we call it lossy compression. Let's see how JPEG works. The JPEG compression algorithm consists of 5 steps, each with a rather complicated name. They are color space conversion, chrominance downsampling, discrete cosine transform, quantization, run length and Huffman encoding. Color space conversion. Our eyes are far more receptive to the brightness and darkness of an image, which is called luminance, and far less receptive to the colors contained in that image, which is called chrominance. Look at this image of a woman. Here the black and white version on the right that shows only the luminance appears to be just as detailed as the full colored image. However, when we look at just the color alone or the chrominance, that our image appears significantly less detailed. JPEG exploits this nuance that our human eyes are not good at perceiving. In color space conversion, the first step is to see the original image that is composed of pixels, and every pixel has red, green and blue components, each with a value from 0 to 255, and the combination of these three values of R, G, B results in color for a single pixel. The process of this color space conversion takes these three RGB values from every single pixel and calculates three new values from luminance, red chrominance and blue chrominance, abbreviated YCRCB. This process is reversible and no data is removed during the conversion. However, the next step, chrominance downsampling, removes a considerable amount of data. In chrominance downsampling, we take both blue and red chrominance component images and divide the component images into 2 by 2 blocks of pixels. Then we calculate the average for each block, removing the repetitive information, and shrink the image so each average value of a 4 pixel block takes up a single pixel. As a result, the information that our eyes are poor at perceiving the red and blue chrominance images are shrunk to 1/4 of the original size, but the luminance remains the same. Now with just 2 steps, the image is half the original size. When reassembling the picture, the blue and red chrominance images are rescaled to match the size of the luminance component, with the RGB values recalculated from luminance, blue chrominance and red chrominance. And because the luminance changes from pixel to pixel, the recalculated RGB values can change from pixel to pixel as well. In the next steps, information is removed, but it is done by exploiting the fact that our eyes are not good at perceiving high frequency elements within images. The next steps is discrete cosine transform, which is called DCT. It takes a finite sequence of data points and expresses it in terms of sum of cosine functions at different frequencies. The code shown here is only one example of an algorithm that implements the DCT transformation on an n by n matrix and is straightforward. Here the time complexity is big O of nm square. DCT goes through each section of the image and finds areas that have a high frequency of alternating chrominance or luminance information. Human eyes are not good at distinguishing high frequency color data such as variations in the shadows created by the leaves of a tree. The image is divided into 8 by 8 blocks and each block consists of 64 pixels. Let's use the luminance component image as our example, but know that the same process happens with the two chrominance components. First step is to assign blocks each with 64 pixels with values from 0 to 255 that represents luminance at every pixel. Next, we shift each value by subtracting 128 from each value, so the range becomes negative 128 to 127. Where negative 128 is black and 127 is white. The resulting values of the 64 base images on the right are achieved by multiplying with the constants from the quantization table. We can rebuild any block of 64 pixels using a combination of these 64 base images by multiplying each image with a constant or a value saying how much of that base image is used. Here we have the table of constants corresponding to the utilization of each base image. This quantization table has higher numbers in the bottom right, where the high frequency that your eyes are not great at perceiving is located, and smaller numbers in the top left, where more distinct patterns are located. After we divide each constant with corresponding value in the quantization table and round to the nearest integer, our block's data looks like this. It has just a few numbers and a lot of zeros. In this step, we are throwing away data, but in reality, we are just throwing away data that our eyes cannot perceive, so we cannot tell the difference. We also use the second quantization table with the chrominance values that are larger, and thus we generate even more zeros in the resulting table. In essence, throughout the DCT and quantization steps, the entire image uses a set of 64 base images which are always the same and two quantization tables, one for luminance and the other for chrominance, in order to transform every 8 by 8 blocks of pixels into just a few numbers and a whole bunch of zeros. These quantization tables are subjected to change depending on the desired quality level. The last step is called run length and Huffman encoding. In this, we list all the values for every block in both the luminance and chrominance images. However, when we list the numbers, we use a zigzag pattern like this because it's more likely that the non-zero numbers will be found appear. Next, we use a run length encoding algorithm where we list the numbers, and then instead of listing all the zeros, we just say how many zeros there are. Perhaps you can see that this list of just a couple dozen numbers is far more compressed than 64 pixels being represented each by a number from 0 to 255. Then we use a Huffman encoding scheme, which is a whole separate encoding algorithm that was covered by Archana already earlier in the presentation. In order to rebuild the original image, we follow the same process but in the reverse order. That is, first we go from run length and Huffman encoding to quantization, and then to DCT, and then to the chrominance downsampling, and last to the color space conversion in order to reverse the order. We can see the final image here. Original file at 100% quality has a file size of 216 KB. At 80% quality, image still looks crisp and clear, and the file size is reduced to be 63 KB, 70% reduction in size. At 50% quality, decrease in quality can be observed, but image still looks great. The file size is now reduced to 38 KB and 80% reduction. At 10% quality or 90% compression, you can observe the artifacts. Reduction in quality is visible to our eye, and the file size is 16 KB, 92% reduction in size. Here are our references for the presentation. Thank you for taking your time to tune into your presentation.